This isn't working again. Okay, so my name is Scott Broussard from the University of South Florida, and this is calculus for fall of 2020. My name is, I already said that. And today we're going to be talking about the product rule. We're going to show you how to use it, prove it, and show you how to prove it, and all of those other things. And we're going to introduce proofs with rabbits. And unfortunately, I left some of the props in my office, including my hat, which is sad. So you're not getting the full experience of this class lecture. So, you know, it is what it is. Anyway, so last time we stated the product rule. But just as a refresher, it's this. So the product rule. So the traditional way of stating is like this, okay? So it's a theorem. Let f and g be defined at an x. Then if f and g are both differentiable at x, then f times g is, this is a bullet point, by the way. Then, that really didn't help, did it? F times g is differentiable at x. And these don't really help, do they? D over dx of f times g of x equals d over dx f of x g of x plus d over d plus f of x times d over dx of g of x. Okay, so that is the rule. Absolutely, the statement of the rule. That's one way to think about it. There's an alternate way of thinking about it. And for the moment, let's think of that as a better way. And I will do examples. Alternate way. Okay. Let U and V move with X, then D U V over dx equals du over dx times v plus, need more space, u times dv over dx. Okay. Now, on both of these things, what do I mean by this? Let's give an example. Let's do d over dx of, evaluate d over dx of sine of x times log of x. Okay. So x is going to take a little trip. By the way, there's chat in Discord and there's chat on Twitch. Please remember the Discord chat is private to the class. The Twitch chat is public. And for some reason this thing just disappeared on me, so I can't see if there's an issue, which is annoying. Okay. There it is. Okay, so uh, let's do this. Now, X is going to take a little journey here, right? Two things are going to happen to X. So let's do X's journey here. Well, let's see. X gets signed. And X also, I take the natural log of him. Okay. So I start X here, and he takes this, I take the sine of X, and then I take the natural log, and then I shove that together into a multiplied thing. So I'm going to call this U and this V. And notice that when X moves, when X changes, U changes. Likewise, when X changes, V changes. So how do we feel about that 1 to 5? All three people that are viewing this, probably including my TA. So 1 to 5, how do we feel about that? The kind of journey of X. Okay. How do you feel about it, TA, since you seem to be the only person that's actually watching live? All right. So X has taken this little journey. Maybe that's overly ambitious. Okay, it is streaming. I just wanted to check. Okay, so I have this X is taking a journey. And so if I take the derivative here, let's see what happens. According to the rule, I'm going to take the derivative of this piece. And then the derivative of this piece. Okay, that's what the rule says. All right. And then what I'm going to do is I'm going to evaluate each of these derivatives. So this becomes cosine of x times ln of x plus sine of x times 1 over x. And I'm just going to leave it like that. Okay. All right. Well, why is that true? Why isn't it just multiply the two together? Well, if we think about this, and this is not the proof, this is just the thought. Okay? I've got this u and this v that both move with x. Okay? Okay? So I've got this u and this v that both move with x. And now what I want to do is I want to look at what happens to them together. Okay? Now, the sum rule, you just add the derivatives. But what happens when I nudge x here? So the question is, what happens to y when I nudge x? So I got x here. X here is going to nudge two things, right? When x moves, v is going to move and u is going to move. And then what I'm going to have is y equals u times v. So the movement, the little nudge that I put in x is going to affect v and it's going to affect u. So the intuition is this, right? So what I'm going to do is I'm going to take u times v. I'm going to u be this distance. I'm going to let v be that distance. And then I'm going to nudge them. And my question is, so give x a little nudge, what happens? What happens to y equals u times v? Okay. All right. So, is it I'm going to have to edit all of this out. Okay. Fix that problem. All right, back to this. So if I give it a little nudge to x, what happens to y equals u times v? All right, so let's see. U is going to go this way. And v is going to go this way. So what I need to do is, the question is, what happens to the change in the total? So what is the change in the total if I give a little bit of nudge here? Okay, so I've got a little change in u, and I have a little change in v, and then I have a change in the total. And that's the change in y. How do we feel about that, 1 to 5? Okay. So what's going on here is I've got a little bit of change in x is going to change a little. And it's going to entice a change in v, and it's going to entice a change in u. So what I've got is y equals u times v. So what I'm going to do is I'm going to give a little bit of a nudge to x, and that's going to correspond to a little bit of nudge in u and a little bit of nudge in v. So the total here, right? So dy, the change in y, should equal, well, let's see. I want this rectangle here, that rectangle there, and this rectangle here. So this change in y bit is that total, right? It's the change in V times U, right? That's this rectangle. I'm sorry, so I've got the change in U times V. That's this rectangle. Plus this rectangle here, which is the change in, which is U times the change in V. Okay? So how do we feel about that, 1 to 5? And then I need to add this little bit extra here. There's a change in V plus times a change in U. Now let's take all these changes to 0. So to begin with, let's do this. Change in Y equals, let's let V equal 2 and U equal 3. And then let's play with the changes here. If this is change in U times 2 plus change in V times 3 plus change in V, change in U. Well, if this thing is 0.001 times 2 plus, let's do 0.02 times 3 plus 0.01 times 0.02. How does these two numbers compare with this number? Let's do it again. 0.001 times 2 plus 0.002 times 3 plus 0.001 times 0.002. Compare these numbers here to those numbers here. Right? How many decimals points is this going to have? Right? This is going to have 1, 2, 3. Right? I'm going to have 0.000. What is this going to be? 0.00002, and compare that to 0.002 plus 0.006. Right? This one's going to have like 4 leading zeros after the decimal point. This one's going to have 2. And then I do it again and again and again. Two terms. So what I'm left with is dy over dx equals du over dx times v plus u times dv over dx plus something that is just nothingness. It goes away. Now, how do we feel about that? One to five. Come on, there's 7 of you now. Well, some of you can give me a feedback. All right. Okay. Let's do a more formal proof then. All right, we want to show that d over dx f times g of x equals d over dx, let's just put the primes in here, f prime of x times g of x plus f of x times g prime of x. Okay? I'm going to leave the strategy blank for a moment. We'll come back to that. But I'm going to use the H definition of the derivative. That's obvious. Okay, so what am I going to do here? So let's see. Fg prime of x. That's going to equal the limit as h goes to 0 of fg of x plus h. And I can't just distribute that. Remember, this is actually not just distributing that. F times g means something. F times g of x equals f of x times g of x. And so f times g of x plus h is going to be f of x plus h times g of x plus h. Now, this isn't multiplication. Keep that in mind. Not multiplication. This means I'm feeding this into that function. So I can't just distribute out those terms. Okay. Minus fg of x all over h. Now I can pull out those terms here a little bit. So I get the limit as h goes to 0, f of x plus h times g of x plus h minus f of x times g of x all over h. Well, now what can I do? I'm stuck, aren't I? I got an f of x plus h here, a g of x plus h here, an f of x and a g of x. Right? I've got some conditions on this theorem. Let's see what those are. I'm stuck. Conditions on my theorem are, let's see. I know f is differentiable at x. No, I'm sorry. I know fg is differentiable at x. Kind of all I have, isn't it? Huh. Now FG is continuous. I do know that f of x and g of x are both continuous. I actually don't know this. I do know that f of x is continuous. I know f is differentiable at x. And I know g is differentiable at x. But I don't have anything else, do I? Well, let's go to the end. How do we feel about these first two steps, 1 to 5? Okay. Let's go down here to the end. I know what the end, I want the end to be f prime of x times g of x plus f of x times g prime of x. So I know that the last line needs to be g of x times the limit as h goes to 0 of f of x plus h minus f of x all over h. And I know that has to be then plus f of x times the limit as h goes to 0 of f of x plus h minus f of x. I'm sorry, these should be g's. G of x plus h minus g of x all over h. Okay? That's what these things have to equal. 1 to 5, how do we feel about that? That's just what the end is going to have to look like. When all is said and done, I want f prime of x times g of x plus f of x times g prime of x. So above that, I'm going to need somewhere I'm going to have the definition of f, somewhere I'm going to have the definition of g prime, and here I'm going to have the f and the g. Okay. All right. I'm not sure what this needs to be here. Well, I'm sure. This is what's going to happen next here. I'm going to do equals the limit as h goes to 0, f of x plus h, g of x plus h, minus f of x plus h, g of x, plus f of x plus h, g of x, minus f of x, g of x, all over h. Well, what did I just do there? You know, I'm just going to do that because I feel like it. Maybe I should justify that step, right? What does this equal? Let's justify that step. What? What are you doing? But look what happened now. Now I've got a piece with f of x plus h. I've got a piece with g of x. Right? Here's a piece that only has g of x in common. Here's a piece with only f of x plus h in common. Right? This I could factor out pieces from. Why would I do that? The answer is that this is a rabbit. Some mathematician came around and pulled out a rabbit. Okay? This right here equals 0. I added something and subtracted it right away. That thing equals 0. But if I do that, look what happens. So now what I'm going to do is I'm going to group things. Right? I'm going to take this term here and I'm going to take out the f of x plus h. So that there came from this term here, and this term here came from there and there. I simply factored. I factored out the f of x plus h in common. And then I'm going to do it again with the g of x. How do we feel about that 1 to 5? That just kind of came from nowhere. As I said, this is a rabbit. Okay. All right, well, now that I've done the rabbit, keep going here. I'm going to break this up using the sum law for limits. F of x plus h times g of x plus h minus g of x all over h. This should be all together, by the way. Plus the limit as h goes to 0 of g of x times f of x plus h minus f of x all over h. Okay. And now I'm going to apply the constant. So here I'm going to apply the product law. I know that this limit over here exists because that's g prime of x, which I know exists. This limit here, because f is differentiable at x, that means that that limit will exist. So how do we feel about that? So what I'm going to do, this is going to be product law. This is a constant multiple. And what I'm going to wind up with is the limit as h goes to 0. I'm going to wind up with the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x all over h plus g of x times the limit as h goes to 0, f of x plus h minus f of x all over h. And so the thing I'm left with that I can't really deal with right now is this piece right here. Okay. Well, actually I can, because I know since f is differentiable, at x, f is continuous at x. So that the limit as h goes to 0 of f of x plus h equals f of x. This term right here is g prime of x. And this term right here is f prime of x. Sorry about that. There was background noise. All right, so I've got all this here. So I get what I want, right? So we can erase this and we'll just line it up like we want it. Which, of course, we'll just pull this in the order that we want it. How do we feel about that proof, 1 to 5? Nobody wants to answer 1 to 5 how we feel about that? So the key step here was this rabbit. I just have to know that piece, right? So when I do my strategy, I'm going to have to say that piece. So let's write up my strategy. My strategy is going to be this. Use H definition. Expand. Add the rabbit to the top and factor. Okay. Apply limit laws. So what do? For my introduction, I'm going to say my want to show, I'm going to say my strategy, and then I'm going to memorize this rabbit. And here's the rabbit. Negative f of x plus h minus, times g of x plus f of x plus h, g of x equals 0. Are there any questions about that? Okay, so now the question is, what do I have to memorize? Because this has shown up on the test before. So the question is, what do you have to memorize? Do I memorize this entire proof? What do you have to memorize? I don't. I do have to memorize something, though. I memorize my introduction. I construct the proof from my introduction. I don't memorize the entire proof. I build it from the introduction. So you don't need to memorize the whole proof, because look at all these things that are in here, right? This is a lot of symbols to memorize. If you try to memorize this, you're going to wind up with symbol jumble. But if instead I memorize this, and I memorize this little chunk that goes in here, I can do it. I mean, it's just too much to memorize, but I don't have to. Okay? I didn't look at this proof before, I've taught it a few times now, but I don't memorize the whole proof. I memorize this. That's the piece. This is a trick, a magician's trick. It's a rabbit. Okay? Some mathematician pulled this out of his hat, and you just have to know it. It should be noted that this was not the first proof. Okay? Took a little while to figure out this one. It's beautiful, it's clean, but it has this piece that comes from nowhere. So I use the definition of the derivative, expand, add the rabbit. Break up in the limit laws. This will happen by continuity. What remains is the definitions of f prime and g prime where you want them. I memorize what the rabbit is. Then when I get graded, there'll be a part in there that says, okay, did you have the rabbit? Let's say I ran out of time, but I just said this. I'd actually get quite a few points, right? I get the H definition of the derivative. I had a strategy. I knew what I wanted to do. And I knew what the rabbit was, because believe me, that'll be on the rubric. But even then, I don't need to memorize all these symbols. The only piece I need to memorize is when I get stuck, add that. And then the rest of it flows. How do we feel about that? 1 to 5. What you need to memorize. You don't have to memorize the whole thing. You memorize what the rabbit is, what the trick is that you need in the proof. Okay. In the notes, there's another one of these. For an exercise, what I want you to do, let's go to the notes real fast. By the way, if you're wondering, everything's going wrong at that house here. The upstairs air conditioning isn't working. And so you heard someone in the background yelling at the AC guy. It's very hot up here. It's like 85 degrees in this room. So that's what's going on in the background. So if you go to the notes, you will find another set in the notes here. Let's see here. I need to turn that on. You will find this proof in the notes where the rabbit is. And then what you're going to find is another proof here where I've given you the introduction. Okay? So the quotient rule you prove the same way. So I'll state that in a minute. But I show you what the rabbit is on the quotient rule. And what I want you to do is I want you to use the rabbit here and try to reconstruct the proof just from the rabbit, just from my summary here. If you can't do it, there's an exercise in the book on page 109. I'm sorry, the proof is actually in the book. So you can look at the book. Obviously, you don't have a hard book. Most of you don't because we're online, and most of you bought the virtual book. But the proof is in the book. So see if you can figure out the proof just from the notes, because you can do it. And that'll give you an idea of what you need to memorize when it comes to doing these. Okay. Are there any more questions about that? All right, well, let me ask you this. What's the point of asking you to memorize a proof, right? It's not that, in 20 years from now, um, a person of your preferred gender is going to come up into you in a bar and go, "Hey, I'll sleep with you if you could prove the product rule to me right now." No, right? We're not doing that. But there is a skill here. Learning, reading an argument, figuring out what the key points of that argument are, and then giving the argument back, rephrasing the argument, and being able to reconstruct the argument in your own words. That's a skill that we're interested in you learning. Okay? So that's why we ask you to memorize proofs. Now, it showed up on the test last semester, showed up on the test the previous semester, showed up the test the previous semester before that. It might not show up this year, but I'm thinking it probably will. Okay. All right. Well, speaking of the quotient rule, let's do the quotient rule. Quotient rule. Let let's see. Let f and g be functions defined at x. Defined at x. If this one has two conditions, f and g are both differentiable at x, and if g of x does not equal 0, then f over g is differentiable at x, and d over dx of f over g of x equals the derivative of the first times the second minus, oh, I'm sorry. Oh, let's try that again. The quotient rule. Let f and g be functions defined at x. If f and g are both differentiable at x and g of x does not equal 0, then f over g is differentiable at x, and the derivative of f over g of x equals the derivative of the first times the second minus the first times the derivative of the second of the bottom, all over g of x squared. Okay. All right, let's do an example. Okay. So let's do d over dx of see the log of x, cosine of x. Oh, let's do this one. No, let's not do that one. Sine of x over x squared. Not at x equals 0. Okay, so here's the journey of x. X has two places. On this side, it's going to get squared. On this side, it gets affected by the sine function. And then I'm going to take the quotient. I'm going to put them together as u over v. So that's the journey of x. So the thing that happens last is where I'm going to start. That's a quotient. So what I'm going to have is the derivative of the top sine of x times x squared. Oh, there's not enough room here, is there? Minus sine of x times d over dx of x squared all over x squared squared. So I'm going to get cosine of x times x squared minus sine of x times 2x all over x to the fourth. And I'm going to leave it that way. 1 to 5, how do you feel about that? Okay. Let's do one more example. Let's do the derivative of tangent. Well, recall that the derivative of tangent is the same as the derivative as tangent here is equal to sine of x over cosine of x. So on our journey of x here, we've got x, sine of x, cosine of x, and then they get quotiented together. The last thing to happen is this quotient. So that's the first thing we're going to evaluate. Okay, so I do d over dx, the derivative of sine, times cosine, minus sine of x times d over dx of cosine of x all over cosine of x squared. By the way, I hate that square notation. Don't do this. Okay? Don't do that cosine squared notation. Do that instead. That will help you. That will save you so much grief in the third module of this class. Is if you, every time you see this square thing, you convert it to this. Because later we're going to have a -1 up here. That's not going to mean the same thing as the exponent. And it's going to drive you absolutely bonkers. So just bear that in mind. It's better to pull that square off onto the side and leave it there. Don't mess with cosine squared ever again. Do cosine of x squared. Anyway. So now I'm going to take these derivatives. I'm going to wind up with cosine of x times cosine of x minus sine of x times negative sine of x. Still all over cosine of x squared. Okay, so now I'm done with the derivative, but I can do another thing here when I simplify. I've got cosine of x squared plus sine of x squared, and if you recall, that equals 1. So, d over dx, tangent of x, equals 1 over cosine of x squared. And if you recall, yes, that's secant of x squared. Secant, who cares? But the point is, now I have a formula for the derivative of tangent. Are there any questions? Okay, well, it's very warm up here, and I have to go apologize to someone. So what I'm going to do is I'm going to stop here. And what I'll do over the weekend, I plan on making a couple more example videos. So I'll do those over the weekend and post them to YouTube. And I need to edit this because the yelling that I had made at somebody should obviously be edited out. And that's it for tonight. Are there any other questions, comments, issues, suggestions, thoughts? Okay, so what we did was we did the power rule and the quotient rule. We proved the power rule. I asked you to go look at the one for the quotient rule. Next time what we'll do is we'll start playing with the chain rule. And I will make some videos for you with more examples of these. All right, that's it for me today. Any other questions? Okay.